Hello there. Another video, it's long overdue, is differentiation with exponentials. Okay, so I'm going to begin with y equals e to the power of x, and I've got a graph sketch here of that very function, y equals e to the power of x. Now e to the power of x is a very special function because when you differentiate it, it's exactly the same. It is e to the x. I'll give you a couple of examples of what I mean by that. If you were to draw the tangent at any point on the curve y equals e to the x, the gradient of the tangent would always be the same as the y coordinate. So here, for example, I've chosen a point when x is 1. So e to the power of 1 is e, so the coordinate is 1e. The gradient of that tangent is e. Okay, a bit difficult to calculate using pencil and paper because e is, of course, an irrational number, but gradient is e. A different example, if you have the gradient somewhere else, like if you have the tangent drawn at the point when x is 2, I'm trying to choose simple numbers, the y coordinate would be e to the power of 2, e squared, and the gradient is also e squared. So no matter what y coordinate we choose, okay, the gradient is always going to perfectly match that. Okay, and the gradient, of course, is dy dx. So we're saying the gradient is always equal to the y coordinate, or in other words, the gradient is always equal to e to the power of x. Okay, so important result, when you differentiate e to the x, you get e to the x. So y equals e to the x, dy dx is always equal to e to the x. Just one of the many reasons why e is a very special number and why we love it a lot in mathematics. Okay, let's have a look at some examples on that. But before, just maybe write down the general rules. I've given it in terms of y and f of x notation. So y equals e to the x, dy dx equals e to the x, obviously the same, just written with the f of x notation. Now here, can you spot why this result is true? If y equals e to the kx, then dy dx equals k e to the kx. Maybe pause the video, have a think about it. Still need a clue? Use the chain rule. Think about how the chain rule works, okay? I'm just going to do it by here. So if you've got y equals e to the kx, where k is any number, let's just say for sake of argument it's 2. So y equals e to the 2x. We want to let u be that power, okay? Remember how the chain rule works? We try and let u be a letter such that it makes the differentiation easier. Because what that means is we're left with e to the power of u. And we can find dy du. It's easy. It's just e to the power of u. If y equals e to the x gives us dy dx equals e to the x, then y equals e to the u gives us dy du equals e to the u. We can differentiate u in terms of x, so du dx is equal to just k, where k is just that constant value. And then the chain rule, remember, dy du times du dx. dy du times du dx. Put these together, you're going to end up with, let me just write it down by here, k multiplied by e to the power of u, where u is kx. So k e to the kx. Hence our result here. Okay. Now, in general, you can just think a bit more quickly if you're doing it in your head. That is to say, when you're differentiating an exponential, e to the power of something, that power will always be the same, it will remain unchanged. Because when you differentiate e to the power of something, you're not changing the power. What you do change is the coefficient of e to the power of that, okay? And what you do is you differentiate the power. So differentiate kx with respect to x, you get k. The reason is because of the chain rule, okay? You've got to let this power, you see, be u. And whenever you're doing u, you're doing du dx, then you're just going to get the derivative of that power. See how that works? Because you're always then differentiating e to the u, so you're just going to be left with this times by this. You'll pick it up, hopefully. You'll pick it up. Examples here. Maybe you work through those. You can do the chain rule for both. Okay, unpause the video when you've got the answers. So here, you can just write it down, dy dx equals, now as I said, the power is always going to be the same. So it will be something times e to the power of 3x. That bit should be easy. With exponentials, I always find differentiating exponentials the easiest thing to do. Okay, the power is not going to change, so just write e to the 3x. Just think about what the front is going to be. You differentiate the power, you get 3. So it's 3 e to the 3x. That's it. Maybe if you didn't do this one, you could do it now. But I'm going to start off with, again, e to the x squared plus 3x. Okay? This might look more difficult than that, but it's still e to the power of something, just something a little bit different, that's all. So e to the power of that, but then differentiate that power, as we did before, you get 2x plus 3, and then that becomes the coefficient. 2x plus 3, e to the x squared plus 3. That's it. Done. This one. Now here's where you have to use the product rule. If you've not seen my product rule video, okay, it should be the one that's just before this video, if I posted them in order, okay. But there in the product rule video, I only did algebraic expressions. Here, we can see how to use the product rule with an exponential as well. So set it up as you would have done in other product rule questions. So u equals 2x plus 3, e to the x squared is going to be v. Differentiate each one at a time. So du dx is going to be equal to 2. dv dx is going to be equal to, now when you're doing this quite often, you can start to actually write it out in order. So that is, differentiate the x squared, you get 2x, and then you've got e to the x squared. Okay, so 2x e to the x squared. Then we can substitute them into the product rule formula. I'm hoping you remember that. V du dx, so that times by that, which is 2 e to the x squared, plus u dv dx, so that times by that. So I'm going to write it as 2x plus 3 e to the x squared. That's it. It's done. If you feel like factorising, you can do. Highest common factor between these terms is 2 e to the x squared. So then that will be 1 plus x, 2x plus 3. Because then that gives us the 2 e to the x squared there. And then plus 2x plus 3 e to the x squared. Maybe just simplify that bracket a bit. So 2 e to the x squared. And then 2x squared plus 3x plus 1. Okay. Maybe the answer does look a bit nicer than this one. Okay, next one. So here, it's a quotient rule question. So you can see what I'm doing, I'm showing you how to use a chain rule, product rule and quotient rule, all with exponentials. Okay. So here, quotient rule, these are rather more obvious to spot because you've got a clear fraction, numerator and denominator. So u is equal to, my board has stopped working, which really irritates me when that happens. It really irritates me when that happens. Right, pause the video time and then I'll sort this out. Right, I'm back again. Just for some reason this pen is just not doing things, so it's fingers time. Okay. Ooh. Right. U equals the top, so 4 e to the 7x plus 2, and v is equal to x plus 3. Then differentiate each term one at a time, so du dx is equal to, so this one, so differentiate the power, you get 7, multiply it by 4, you get 28. So 28, and then of course e to the 7x plus 2, remember the power does not change. And then dv dx is equal to, just 1, that's simple, isn't it? So then we use the quotient rule formula. So dy dx equals, you must get the order right, v du dx first. So v du dx, so I'm going to write that as 28x plus 3, e to the 7x plus 2, and then subtract u dv dx, subtract that times that, 4 e to the 7x plus 2, and then all over v squared x plus 3 squared. And that's it. That's that question done. You can simplify it a little bit by just maybe factorising the numerator. So we can take out a factor of 4 between these two numbers, and e to the 7x plus 2, which means we'll have 7 to get 28, x plus 3, and that's fine, and then minus 1, all over x plus 3 squared, and I can't go on that anymore. This is the thing when you get to this sort of stage of differentiation, you need quite a few lines of working. I'm kind of limited by my board space, so I'd write the final answer here. So 4 e to the 7x plus 2, and then 7x plus 21 minus 1, so plus 20, all over x plus 3 squared. Okay, that's it, done. Very good finger work, wasn't it? There we go. All right, great. Next, differentiation when e is not the base. Okay, a little bit harder. Okay, you need to know how to show these results for the A-level exam, but if you can remember them, if you can memorise results, that would be great, because when you're asked just to differentiate that, you can just write down the answer. All right. However, if you don't memorise it, if you don't remember how to do it, you've got to be able to know the method of doing it. Okay. I've got two methods to show you. One of them is for if you've done P4, which I'm guessing you might have done, you might have not done, I don't know. It wasn't much of a guess, was it? But there's a P3 method as well. So here we go. We'll do the P3 method first. Actually, I could just, yeah. Oh, that's not working either. Oh, I've messed that up. Don't want to go, is it? I'll leave it. Right, so here. So if I were to ask a student in year 12 to do this, they would say, but sir, I can't do this because x is a power. Okay, that's what makes this question more challenging. Okay, x is a power. So using logarithms, we can actually use the power rule logarithms to bring the power down. What type of logarithms are we going to use? Natural logarithms, of course, yes. Yeah, e is the most natural base to take in logarithms. So we do the natural log of both sides. So natural log of y equals natural log of 2 to the power of x. The reason is because you can use the power rule, bring the power down, so it becomes x natural log of 2. Okay. Now, if you were doing P4, you could then just do something different to what I'm about to show you. All right. But what we can do next for P3 level mathematics is make y the subject. And if we make y the subject, we can do e to the power of to both sides. Remember, e to the power of is the inverse of the natural log of something. So you've got y equals e to the power of all this, x natural log 2. Now we use the chain rule to differentiate that. So dy dx equals, and then obviously I have e to the x natural log 2, multiplied by the derivative of the power, which is just natural log 2. Remember, natural log 2 is just a number. So you've got a number times by x, so the derivative is just a number. So it's going to be e to the x natural log 2, natural log 2. The reason I write it that way is because, just to see if my pen function can come back. Okay. If I wrote it like this, natural log 2, e to the x, natural log 2, can you see it's not clear where the natural logarithm starts and ends? Well, it's not clear where it ends, it's not clear where the e to the power. So am I doing all of that, for example? Or am I doing just that times by this? Can you see, written like this, it makes it absolutely clear. And in mathematics, we need to be absolutely clear when we're writing stuff down. So e to the power of this multiplied by natural log 2. So that's the reason why I've written it in that specific order. Okay. Right, continuing on with it then, notice that that is just the same as y. E to the power of this is just the same as y. So you can rewrite it as y times natural log of 2. And y is also the same as 2 to the power of x. Okay. So you can write it as 2 to the x natural log 2. Remember, when we're differentiating, we're finding an answer in terms of x. We need to do y dx. So that's it. So as I said, you can either memorise that result, which I strongly recommend, or you need to know how to do it. Okay? It could be a show that or a proof question in the exam anyway. Okay? But if you just ask to differentiate, for example, let's just do this simple example. If you ask to differentiate this, 3 to the power of x, you can just remember that result. Just replace the 2 with the 3. So instead of 2 to the x, it's 3 to the x. Instead of natural log of 2, it will be natural log 3. Okay? In the exam, far quicker just to write down the answer if needed. Okay? If you don't need to bother with the proof. Maybe I'll show you the P4 method now in case you've done P4. So from this stage here, we would differentiate implicitly. Okay? If you've not seen implicit differentiation, I might have another video on it somewhere. Okay? But I'm not about to explain implicit differentiation in this video. Okay? So ignore this little bit if you've not seen yet the P4 method of implicit differentiation. So you differentiate that, it'll be 1 over y dy dx equals the natural log of 2. And then dy dx is equal to y natural log 2. You can see we've got exactly the same result as that already. Okay? And dy dx is equal to 2 to the x natural log 2. Okay. But that's the method you're probably happiest with if you're seeing this for the first time. In general terms, a to the power of x, where a is any number. When I say any number, okay, I mean not 0, because 0 to the power of x is 0, okay, simple case. So I'm just talking about any number, whether it's a fractional number, okay, or a positive number, okay, it's a 2 or 3 or half, something like that, okay. Check yourself if you want to see if it works with negatives. But look, here we are, same rules again. So natural log of both sides, bring the power down, and then y equals, make y the subject, e to the power of, differentiate that, chain rule, so it becomes that. And then this is the same as y, this is the same as a to the x. So here you go, your general standard result. Okay. In case you want to see it, same again with the P4 method using implicit differentiation. Differentiate that implicitly, 1 over y divided x. Divide x equals that, this. Okay. Happy with that? Good. Okay, well, I'm hoping you found that extremely useful. All right. Maybe before I go, before I say bye-bye, I just think of this one, because this seems to catch students out all the time. How would you, for example, differentiate this 2 to the negative x? Okay. Because you might think, oh, he's not actually given us an example like this before. It's quite simple. Okay. What you do is you rewrite it as 1/2 to the power of x. And the reason for that is this here you can write as 2 to the power of negative 1 to the power of x. Remember expanding the brackets there with the indices? That's the same as 2 to the negative x. 2 to the negative 1 is the same as 1/2. Okay, just maybe remember that, because negative powers do come up sometimes. Okay, and then a is just a half, so your answer would be 1/2 to the x natural log 1/2. Okay, just thought I threw it in there while I remembered it. Hope you found this video useful. Thanks for tuning in. See you again.